Assalamu alaikum. How are you doing? Today we are going to wrap it up and finish talking about determinants. There are a few ideas left. We finish them. I give you few examples, few exercises, and we will be done with this chapter, determinants. Okay, determinants and actually inverse of matrices. Okay. The first thing I'm going to talk about is another method for solving linear systems that have unique solution. So we said when you have a linear system, you can write it in matrix form as AX equals B. Okay, so here your matrix A is an n by n matrix. Okay, now if this matrix A is invertible, then X, if A is invertible, then X equals A inverse B. Now, how do you find that? We said you have two ways to do it so far. One way is you do it using elementary row operations and echelon form or reduced row echelon form, and you get X. The other way is to find the inverse of A, and you just multiply A inverse by B. Okay? So far you have two ways of doing that. Of course, you have the third way, which is to use the computer, but we're talking about the ways in which you can do it by hand. Okay? Well, there is another way that is interesting, and that is named after Cramer, a mathematician in the 18th century, I guess. That is very simple, very nice in writing a formula, but still it needs some computations. So let's see here. Cramer's rule, it works whenever A is invertible. Okay? So in that case, this means determinant of A is not 0. Okay? So let's see, how does it work? I'm going to do it for 3 by 3 matrices, or systems of 3 equations and 3 unknowns. Then after that, you can write it in general for any system of n equations and n unknowns. So let's say here we have A11 x1 plus A12 x2 plus A13 x3 equals B1. Here A21 x1 plus A22 x2 plus A23 x3 equals B2. And here A31 x1 plus A32 x2 plus A33 x3 equals B3. And the coefficient matrix here is A equals A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay? So Cramer's rule, so here we are assuming determinant of A is not 0. We're assuming that. If determinant A is not 0, it doesn't work. Cramer's rule here, or the method that I'm going to talk about now, does not work. Okay? It tells you the following. It tells you x1 is going to be determinant of this matrix. You write this column in place of this column. B1, B2, B3, and here A12, A22, A32, here A13, A23, A33, and you divide that by determinant of A. That is x1. x2 is determinant. Now you can guess. What do? We replace the second column by this column. So here, A11, A21, A31, here B1, B2, B3, and here A13, A23, A33. Divided by determinant of A. X3 is determinant of, again, what do? You have A11, A21, A31, here A12, A22, A32, and here is B1, B2, B3, divided by determinant of A. It is very simple formula. That's what is good about Cramer's rule. It gives you the answer in a formula. But if you think about it, in terms of computations, you have determinant of A that you need to evaluate. You have 1, 2, 3 other determinants that you need to evaluate. Okay? Now, for 3 by 3 matrices, that is manageable. Now, think about if we do it for large systems. If this matrix is 10 by 10, okay? So what are you going to get here? You are going to get here 10 determinants in the numerators, and you are going to get determinant of A. And each one of them is 10 by 10. So that is a lot of computations. Okay? So it has some good features. You write the solution as is in a formula. But the disadvantage here, you have a lot of computations to do. Anyway, we give you that as a method, and it's up to you. Which method you use, it's up to you. If you ask me about an example here, let me give you this example, and then we do it together. Solve, use Cramer's rule. Cramer's rule to solve 1, 0, negative 1, 0, 1, 2, 0. Let's see here, negative 1, 1, 1. Here x, 1, x2, x3, and here 1, 0, 1. Okay, well, I did not think about this. Let's see, is determinant of A, is A invertible or not? Well, if you check the determinant of A here, so this is A. So the determinant of A is, can we quickly find the determinant of A here? So that is going to be, I'm going to use the first row here. So that will be 1 multiplied by 1 minus 2, negative 1, then 0 minus 1 into 0 minus minus 1. So what is that? Negative 2. Double check, please. 1, here 1 minus 2, that is negative 1, and then 0, then here negative 1 multiplied by 0 minus negative 1, that is 1. So minus 1 times 1, so that is negative 2. So that is not 0, so yes, we can use Cramer's rule. Okay, so here, if we go to this, in this example, in our example, you have x1 equals determinant of over negative 2. Determinant of what? You have 1, 0, 1, 1, 0, 1. You have 0, 1, 1. You have negative 1, 2, 1. Then you have x2 equals determinant of 1, 0, negative 1, 1, 0, negative 1, here 1, 0, 1, and here negative 1, 2, 1. Again over negative 2. Then x3 equals determinant of 1, 0, negative 1, 0, 1, 1, and here you have 1, 0, 1 over negative 2. So you evaluate the determinant in the numerator in each one of them. What do you get? Again, let's do that quickly. So here you have 1, and here 1 minus 2, that is negative 1 times 1, that is negative 1, that is 0. Then you have negative 1 times, this is 0 minus 1 over negative 2. Am I correct? So what do we have here? We have negative 1, we have a plus 1, so this is 0. x2, what is x2? This is 1. Why don't we use here the second row? The second row, this is positive, negative, positive, negative. So we have negative 2, 1 minus negative 1. So that is 1. Again, we do this here, 1 minus negative 1. So what is that? Negative 4 over negative 2, and you get 2. Here, what do you have? I'm going to use the first row here, so we have 1, 1 here, that is 1, that is 0, that is plus 1, multiplied by 0 minus negative 1, 0 minus negative 1. So this is, what is that? We have 1 here times 1 plus 1, 2 over, that's negative 1. So here is the answer, x1, x2, x3. It is 0 to negative 1. Let's double check here. 0 to negative 1. 0 to 0. And here negative 1 times negative 1 is 1. So the first equation is correct. You can double check the other equations. I'll leave it for you to double check that. Okay? So here is a Cramer's rule, and here is how you can use it. Okay? Of course, here I've chosen this example in a nice way so the computations are not too bad. But you can try it for other exercises, and you see whether you find it too much computations or you find it acceptable. Okay? Again, let me stress here. This works when the determinant of A is not 0. If the determinant of A is 0, don't even think about it. Okay? All right, so this is about Cramer's rule. Now, let me talk about other properties of determinant. Let me talk a little more about finding the inverse of an invertible matrix. So, we talked about how to find A inverse when A is invertible. When determinant of A is not 0. And the method we discussed, it was you put your matrix beside the identity, you do elementary row operations till you get reduced row echelon form, and from there you can see the inverse of your matrix A. Do we have another way of doing it? Yes, we do. And that is using the cofactors. Remember, we discussed minors and cofactors, correct? So, for recall, minors, and cofactors. So we said if you have a matrix A, A11, A1n, AN1, ANN, you can write a matrix of minors. M11, M1n, MN1, MNN. And we said the minors, you get them by using determinants. So if you remember, we said M11, you find it by covering row 1 and column 1, and you take the determinant of what is left. Correct? So here, each one of those is a determinant of, this is n by n. Each one of them is a determinant of n minus 1 by n minus 1 matrix. And we said from this, you find the matrix of cofactors. What is the matrix of cofactors? The matrix of cofactors is C I j equals negative 1 exponent I plus j m I j. So you take mij from here and you see what is the sign. So here you get C11, C12, C1n. And here Cn1 and here Cnn. Okay? That is called the matrix of cofactors, or the cofactor matrix. Okay? So we already talked about that. Now, we define something called the adjoint of a matrix. Adjoint of A. So let me repeat myself. You have a matrix A. It's n by n matrix. Okay? And the determinant is not 0. From this, we found a matrix called the matrix of minors. Okay? And from this, we get a matrix, the cofactor matrix, or the matrix of cofactors. Okay? Now, from this, we get a matrix called the adjoint of A. The adjoint of A is C transpose. Okay? C transpose. Now, A inverse is adjoint of A divided by determinant of A. And that is a nice formula for A inverse. What is good about it? It will give you A inverse as a formula here. Okay? In echelon form, when we do it using, when we use elementary row operations to get the inverse of a matrix, you don't have a formula. But here, you have a formula. Okay? Again, that is nice, but think about now the computations. From here to here to here to here. There are a lot of computations involved in this. Let's do it in one of the examples. And I'm going to take here again. I don't want to take long example because all examples are the same. It's just the question is, do you have nice computations or do you have ugly computations? So let's take this example. A is, I'm going to take this matrix. The determinant here is not 0, so let's find the inverse. 0, 1, 0, negative 1, 1, 1. We found the determinant already, correct? The determinant is 2. Determinant of A is 2, not 0. So this matrix is invertible, correct? So here's the question. Find A inverse. And let's do it using this method. Okay? So what's the first step? So here is your A. The first step is to find the matrix of minors. So let's do that. M11. What is M11? U. Cover this. You cover this. You have 1 minus 0. This is 1. You come to this, cover this, cover this. You have 0, and here 0. You have 1 here, cover this, cover this. You have 0 minus negative 1, that is 1. Then here, have this, this. So here 0, here minus 1. Now here, cover this, you have 1 minus negative 1, that is 2. Cover this, you have 1 minus 0. We come to this, 0 minus 1. Here, 0 minus 0. Come to this, cover this. You have 1 minus 0. Double check that, please. So this is the matrix of minors. Now, the cofactors, they are going to be 1, 0, 1. That is negative, so that is going to become positive. That is 2. That is negative 1. And here positive, negative, positive, so that is negative 1, 0, 1. Double check, please. All right. Now, what is the adjoint? The adjoint is going to be here. It's going to be 1, 0, 1. 1, 2, negative 1. Negative 1, 0, 1. What is A inverse? A inverse now. Here it is. A inverse is adjoint of A over determinant of A. Determinant of A is 2, so this is 1/2 multiplied by 1, 1, negative 1, 0, 2, 0, 1, negative 1, 1. Here it is. Okay? Double check that. If you multiply this by this, you should get the identity. So double check. Is that true? If not true, it means we are doing a mistake somewhere here. Okay? And I'll leave it for you to double check, and if there is a mistake, please find it. Okay? I can see here, for example, when you multiply this by this, you get 2 over 2, which is 1. So that is the first step to check that, and it is fine. Okay? But I'll leave it for you to double check. All right, so this is another method for finding the inverse of an invertible matrix. Here you have it, and it is up to you to use it or when to use it. Okay? After you practice few exercises, you can see here, in some cases, like in this example, it is not too bad. But if you have kind of a weird matrix, you can expect a lot of computations. All right. So I covered all the ideas here. Let me here ask you a few questions, and let's do them together. By the way, you need to recall some determinant properties we discussed last time. So here, recall. Number 1, determinant. You know determinant, sometimes I write it capital D, sometimes small d, so it should be fine. So determinant AB is determinant of A, determinant of B. And that is something we verified last time. Number 2, we said if K is a scalar and you multiply it by a matrix A and you want the determinant, then A here is an n by n matrix, so this is going to be K exponent m determinant of A. Okay? So those two properties are crucial here, and we already discussed those two. Now, here is a question. Suppose A and B are 4 by 4 matrices. Such that determinant of A is, let me take this one. This is a 3 and determinant of B is 4. Find or evaluate one determinant of 2 A B inverse and 2 determinant A squared 2B inverse. So let's do the first one. Determinant 2A B inverse. Well, K is 2 here. A and B, they are 4 by 4 matrices. So what's the first step? The first step, when you take this 2 out, it is going to be 2 exponent 4. So determinant 2 A B inverse is going to be 2 exponent 4 determinant A B inverse. Correct? Now, using this property, we can say this is 16 determinant of A determinant of B inverse. By the way, is B invertible? We're saying B inverse. Is it invertible? Yes, it's invertible because we are already here saying determinant B is not 4. Determinant B is not 0. Okay? So, yes, B is invertible. So that's the reason here we are saying B inverse. Now, determinant of A, you have it. It is a 3. So this is 16 times 3. Now, what's determinant B inverse? Determinant B inverse is 1 over determinant B. So this you can write it as number 3 here. Determinant of B inverse. We already talked about that. It is 1 over determinant of B. So that is going to be 1 over 4. So the answer is 12. Think about it. Is it clear? All right. If it's not clear, you ask me in the live session when we meet. All right. What about the second one? Again, we do the same thing here. 2 determinant of A squared 2 B inverse is determinant of A squared determinant of 2B inverse. And that is determinant of A squared, that is determinant of A times determinant of A, correct? So determinant of A is 3, so this is 9. And this is 2 exponent 4. And this is determinant E inverse. So what is that? Again here, this is 1 over 4. You cancel it with 4 from here. You have 4 times 9, 36. Okay, I have a question for you. What if I change this and I put here the inverse instead of B inverse if I put it here? So here, let me write it down here. If I ask you a third question, determinant of A squared to B inverse like this. Is it the same question? Obviously, it's not the same question. Here, the inverse, it was for B. Here, the inverse is for 2B. Correct? So that should make a difference here. Well, let's do it. What do you get? You get determinant of A squared times determinant of 2B inverse. Now, 2B inverse. Think about it. That is going to be 1 over determinant 2B. So this is going to be 9, 1 over determinant of 2B. And now you take this 2 out, it will be 2 exponent 4. So this is 9 over 16, or let me write it as 2 exponent 4, so you can see it. And now determinant of B is 4. So that is 16, 64, 9 over 64. Okay? All right, let's take another example. Or another question. Question. Let A, B, and n by n matrix suppose that summation A, I, j from 1 to m equals 0 for all I from 1 to n. What can you say about determinant of A? Well, think about this question. Let me give you 1 minute to think about it. That is clear, n by n matrix. What does this mean? It means here, when you sum each row, so here is your matrix, A equals A11, A12, A1n, A2, 1, A2, N, AN1, ANN. When you sum each row, you get 0. Again, you have an n by n matrix. When you sum along the rows, you get 0. What can you say about the determinant of A? Well, this is a tricky question. I mean, it is not hard, but it is tricky. If you think about it in a straightforward way, you are going to get stuck. Because this is n by n. How are you going to write the determinant? However, if you think about what we are saying here, isn't that like when you multiply A by a vector of ones? What happens when you multiply this by this? You are going to multiply this row by this column. So what do you get? You get the summation of the rows. And this, because it is given as 0, so this is 0, 0, 0. So here, if you think about this question here, what are we talking about here? We are talking about a system like this. A multiplied by this column vector, you get this column vector. Well, think about it now as a linear system. A, x equals 0. It's a homogeneous system, correct? Now, this x is going to be this, 1, 1, 1, 1. What does that mean? It means this system, this homogeneous system, it has a non-trivial solution. We know a homogeneous system always has the trivial solution. But now, we are seeing that this homogeneous system has a non-trivial solution. This homogeneous system has a non-trivial solution. What does that mean? When a homogeneous system has a non-trivial solution, it means this matrix A is non-invertible, because if it is invertible, the only solution is the trivial solution. If A is invertible, the only solution is the trivial solution. So in this case, it must be non-invertible. So that's it. We got the answer. Therefore, A must be non-invertible. What does that mean? It means determinant of A must be 0. Very simple, but very interesting idea here. Okay, we connect the ideas together. We connect linear systems with matrices, with determinants, and the idea is very interesting. All right. One last question. So here, last question. Let A be an n by n invertible matrix. What can you say about determinant adjoint? Again, adjoint, sometimes you see it in capital A, sometimes in small a, so that's fine. Adjoint A. What can you say about determinant adjoint of A? Let's see. Remember what we said about A inverse. We said A inverse equals adjoint of A over determinant of A. Correct? Now, here we are saying invertible n by n matrix. So this is something we can use here, correct? Now, if you multiply, well, this here, determinant of A, this is a number. Why don't you think about this as a constant k? Okay? So here you have k A inverse equals adjoint of A. Once you do that, then it becomes clear to you what is determinant of adjoint A. It is going to be determinant of K A inverse. And now this, you know it, correct? Well, this is going to be K exponent n, and determinant A inverse is going to be 1 over determinant of A. But now think about K. What is K? K is determinant of A. So you have determinant of A exponent n over determinant of A. So what do you get here? You get determinant of adjoint A, and the conclusion is determinant adjoint A is K exponent n minus 1 or determinant of A exponent n minus 1. So this is going to be this. Determinant of A exponent n minus 1. So this is the relationship between the determinant of the adjoint and the determinant of A. That's interesting. That is not easy to see right away, okay? But if you use this, it is very simple, very straightforward, okay? Now, of course, if A is not invertible, we cannot use this. All right, so that's it. That's it about determinants. And after this lecture, we are going to start talking about very interesting subject called vector spaces. Still, we are going to relate that with linear systems and with what we did. But basically, we are done with the computational part in this course. So we are going to move to something that is less computational, but it has very interesting ideas. All right, that's it for today. Thank you guys for listening, and see you in the next lecture.